discovering electrons led to more questions. Well, there's negative electrons inside. We know that atoms are neutral. There must be something positive in there to balance out the negative charge. What is it, and how do those oppositely charged things fit together? Are atoms just like a jumble of a whole bunch of different particles? How many kinds of particles are they? Are they solid spheres? Do they have some internal structure? Yeah.
So are they saying that when they did the cathode ray experiment, that's how they got to know that the electrons exist? Or
Yes.
did they already know about it?
They did not know that electrons existed.
Oh, okay.
And so when they made that cathode ray and found the mass to charge ratio, they were able to realize that it was much, much smaller than any known atoms.
Mm-hmm.
And that was really quite shocking.
Okay.
Yeah, really shocking. So people started coming up with ideas. So Thomson, the guy who did this cathode ray tube experiment, he came up with what's called the plum pudding model. Now, in the United States, we don't eat plum pudding, right? We like, what is that? It's a British thing. The closest thing we have to plum pudding would be like a blueberry muffin. Okay, so if you think of a blueberry muffin, but it's nice and round, there's blueberries inside, and they're just kind of randomly distributed, but they don't move, right? They're just stuck in there inside the muffin part. So this is his idea. You have to start somewhere. So his idea was that there was a sphere of positive charge. I wasn't sure what that was, but that's like the muffin part. And it's got electrons that are negatively charged, just kind of scattered throughout. And those are like the blueberries in the blueberry muffin. Radioactivity was used to discover the other particles, and so we need to just mention what it is. Radioactivity is the emission of small energetic particles from the core of certain unstable nuclei. It was discovered at the end of the 19th century, so in the 1800s. And so with radioactivity, they were able to bombard atoms with these radioactive particles and see what happens. So 3 main types: alpha particles, beta particles, and gamma rays. The alpha particles have a positive charge on them, and they are the biggest. And then if you take Chem 1B, you'll learn a lot more about radioactivity, but that's all we need for now. So Rutherford was one of Thomson's students. He did an experiment trying to support Thomson's plum pudding model. So he took positively charged alpha particles and shot them at a very, very thin sheet of gold foil. So in the plum pudding model, with the mass and the charge spread all around in the atom, you would expect that the particles would go through the foil. It's all spread out. So that's what they were expecting. This is an illustration of the setup. So this is a source of alpha particles, and you shoot the alpha particles at this gold foil, and then you have a detector around the edge to see where those alpha particles end up. And what they expected was that they would go straight through. Most of them did. But some of them bounced back. And that was shocking. It's like, okay, we need to rethink this model here. How is this happening? Rutherford said that the bouncing back was about as credible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So, a big gun with a shell that's 15 inches, right, longer than a regular piece of paper. You shoot that at a piece of tissue paper, and what do you expect? It's just going to go straight through, right? No, it bounces off the tissue paper and comes back and hits you. Not possible, right? that's how surprising this was. It was shocking. So obviously the plum pudding model wasn't quite right, so they came up with a new model. So from this experiment, Rutherford concluded that matter must not be as uniform as it appears. Here's the plum pudding model where everything's distributed evenly and alpha particles should just go right through. So it can't be that uniform. It must have a lot of empty space, but have some small areas that are really, really dense, where most of the matter is. And so this is the nuclear model, where we have a nucleus where most of the mass is found, and then outside of it we have this electron cloud, which is mostly empty space. So what was happening in his experiment is that most of the alpha particles just passed through this electron cloud. But if one hit the nucleus had a charge and was very massive, and so it would bounce off. So let's think about a volleyball net and shooting airsoft pellets. You know what those are, little tiny plastic pellets? Supposedly not dangerous, so you can shoot your brother. If you shoot tiny little pellets at a volleyball net, most of them are going to go through, aren't they?
Mm-hmm.
But if you happen to hit a string, they'll bounce back. And so that's kind of the idea here. Inside the nucleus, we have protons and neutrons. We'll talk about the neutron in a minute. So this led to the nuclear theory of the atom, and there's three basic ideas. Most of the atom's mass and all of the positive charge is contained in a small core called a nucleus. Most of the volume of the atom is empty space in which tiny negatively charged electrons are doing something. There are as many negatively charged electrons outside the nucleus as there are positively charged particles, protons, within the nucleus, so that the atom is electrically neutral. These guys spent a lot of time thinking about things. So that model was very successful, but it was incomplete. So they were able to determine that hydrogen contains one proton and helium contains two protons. So you would expect the mass of helium to be twice as large as hydrogen because it had two protons to one proton. But helium is actually 4 times heavier than hydrogen. So there's got to be something else in there. And so Rutherford and one of his students, James Chadwick, figured out that unaccounted for mass was due to the neutron. Neutron is a neutral particle within the nucleus. So neutrons are neutral. They have no electrical charge. Neutrons are similar in mass to a proton. For our purposes, the difference is nothing to talk about. The reason the helium atom is 4 times heavier than the hydrogen atom is because it's got 2 protons and 2 neutrons. So it actually has 4 of these massive particles instead of 1, so it's 4 times as heavy. The nucleus is extremely dense, and that's really an understatement. You've got more than 99.9% of the mass of an atom in the nucleus, but it occupies very little space. And so your book has some analogies and things to help us think about it. So if we think about a cloud, or we're more familiar here with fog, right? In the winter we have fog. A fog is really just cloud down here among us, messing up our lives. The electrons are like the little water droplets in fog. They have negligible mass, but they're spread out over a large volume. And as a result, we have a hard time seeing through the fog. And yet, fog and clouds are mostly empty space, right? You can just walk through it. There's no resistance. You'll get a little bit damp walking through it, but it's mostly empty space with these little tiny droplets of water suspended. Atoms also are mostly empty space. So if the nucleus was the size of a period, like in a textbook or something, the electrons would be 10 meters away. This is 1 meter. So like maybe from here to the door. A period. I can't even make it with chalk, it's too small. The electrons are over there by the door, and in between is literally nothing. If, you can't, but if you could take nuclei and without the electrons and all the empty space and just squish them together and make something as big as a grain of sand, that would weigh 11 million pounds. A grain of sand, 11 million pounds. It's just like crazy dense. It's crazy.
Is there like a limit on how dense something can be?
That's a good question. Is there a limit on how dense something can be? Well, I can't speak for things like black holes. Yeah, not an astronomer. But the nucleus, I think, is really as dense as you could possibly get. So matter is mostly empty space. And yet, this bench feels pretty hard, doesn't it? So let's imagine scaffolding, or like a jungle gym, the size of a football field and 100 stories high, right? It's composed of bars of metal in, rectangles and stuff, and it's making this big scaffolding structure. And just to give you some idea, here's a man down here. This is big. This is really big. So 10 stories high and taking up a whole football field. It's mostly empty space, right? It's just got these bars of metal, and everywhere in between is empty space. But if you went high up in the air in an airplane and looked down at it, kind of like we're looking at it here, it would look solid, right? Because there's enough of these bars that they get in the way and you can't see through it. Just like the little droplets in the fog, right? They don't take up very much space, but you can't see through it because there's so many of them spread out in different places. So when you tap your finger on the table, it's like taking one of these giant scaffoldings and crashing it into another. They're mostly empty space, but they don't fall into each other. But then that makes you think about some of the, science fiction stuff, like, well, could you find a way to just like go through matter? Right? I mean, there's enough space in there that you should be able, two things could just pass through each other. So why does matter appear solid? It's because the variation in density is too small for our eyes to detect it.